I want to talk to you today about calculating standard cell potential. So the equation that you see is the equation that most students wind up with. This is the equation that's in your textbook. This is the equation that's in ALEKS. So this is the standard cell potential of the entire cell. You put the two half cells together is the standard potential from the cathode minus the standard potential of the anode. Now the part that this doesn't say is that both of these are actually going to be your standard reduction potentials. So both of the numbers from the previous equation come straight off of the table that we're using. So the whole reason why you have that minus sign in there is because you're taking into account that one of them is the reduction and one of them is the oxidation. But oftentimes the way it's memorized is cathode minus anode. But the part that's not mentioned is that both of those come off of the exact same table, which is the standard reduction table. Now, with the standard reduction table, this is the table that's given in your book and in the notes, and you can always orient yourself by looking at the top and the bottom, and what you should see is you should see fluorine at the very top, which is much more likely to be reduced. Fluorine's always looking for extra electrons. That's why it's the most electronegative element. And down at the bottom, you can see lithium. Lithium is always willing to give up electrons or always ready to be oxidized. Now, there's a different equation that looks very similar but is distinctly different, which looks like this. So now we have still the same idea, the standard cell potential, but now we're looking at it's the standard reduction potential plus the standard oxidation potential. So now that minus sign has gone away, except it really hasn't. Realize that what's happening here is the table is given in reductions. Everything in the table is a standard reduction. If you were to calculate the standard oxidation potential, it would have the opposite sign. You would flip the reaction around, and as you flip the reaction around, you would flip the sign. So if you're looking at the standard reduction potential plus the standard oxidation potential, this is assuming that you're going to flip the sign of whatever's at the anode. If you take a look back at both equations, you'll find they actually do the exact same thing, which is take into account that whatever is happening at the anode, whatever is being oxidized, actually will have a reversed sign from the way you see it on the table, since the table is all about reductions. Let's do an example. Let's say that I want to look at a copper half cell with a zinc half cell. So for copper, we're going to use a copper 2 plus to copper solid. This is all just part of the example, so we would give you the information for this, and a zinc 2 plus to zinc solid half cell. So I'm going to look all over this table and find the two values that I need, and I'm going to pull them off the table. So as I pull them off the table, I have these values. When I look at these values, these again are exactly off the table. What I can see is that copper is higher up and zinc is lower down. So copper, being higher on the table, should be more likely to be reduced, zinc more likely to be oxidized. So this would label my cathode and my anode. From here, I could use my cathode minus anode equation, in which case I would merely take one, subtract the other, and we're done. Now this does require me to take a look at which one is higher up on the chart so that I know which one is which. So I am still doing an evaluation to know what has to be subtracted. So this would still give me one answer. So this is one way to do the math. Looking at it the other way, what would happen is as I pull these values off of the table, these are both being pulled off of a reduction table. So as I look at these values, these are both the standard reduction values. But what I know is happening is I know that zinc is actually oxidized. This is from the same logic that we know that the zinc is a more negative value, it's lower down on the table, therefore it is more likely to be oxidized. So if we're using our other equation, this means that I need my oxidation potential, which is the flipped sign of the reduction potential. From there, I merely add the two values together, and you'll notice I get the exact same number. Again, I know that this seems confusing because they're two very similar equations, yet they're different. Again, all you need to do is choose one of them. As long as you have a way to calculate the standard cell potential, you're going to be just fine.